Combinations. So when order doesn't matter, combinations are used instead of permutations. So for example, how many ways can two people be selected from five people? So these are all unique people, these five people, and you want to select two of them. So it's kind of like you've got A, B, C, D, and E. There's your five people. And um, if you select A and B, that's exactly the same as selecting B and A. So for these, we use combinations instead of permutations. And there's a formula and a notation for combinations, just like there was for permutations. And this is what it is. We use NCR instead of NPR for combinations, and NCR is equal to N factorial. It's very close to what we had with the last one, N minus R factorial, but now we also divide out by R factorial. So for the question that we just had here, if I create a little bit of extra room, I have five people, so that's the n, and I have two people, so that's the number that I'm selecting. So I do 5 choose. That's another name for C, is sometimes people use choose. 5 choose 2. And so if I use my notation, that's 5 factorial over 5 minus 2 factorial times 2 factorial. So that's 5 factorial over 3 factorial 2 factorial. And this actually looks a little bit similar to choosing identical objects. You've got 5 different objects. 3 of them are objects that they're people you do not select. So you say no, no, no to those 3 people, and these are people that you say yes. So it's kind of like you've got 5 people, and you say, oops, I did that backwards. Say no, you don't want 3 of them. Yes, you want any 2 of them, and the 2 that you get, it doesn't matter. They're essentially identical people. So you have 5 objects, and you divide by 3 and divide by 2 factorial. So there are some similarities between these different ways of attacking questions, and this is actually what causes the most problems for students, is there are multiple ways to get to the right answer. Of course, if you do this, you get 120 over 6 times 2, which is 12, and there are only 10 ways to take 2 people from 5 people. Let's see what happens if we do 3 people selected from 5 people. Well, that's 5 people, choose any 3 of them, so 5 factorial over 5 minus 3 factorial, and then 3 factorial, which is 5 factorial over 2 factorial, 3 factorial. Wait a sec, that's exactly the same as what I just had, and hopefully you can reason why. Think about this one as you had 5 people with any 2 being selected, and now you have any 3 being selected. You can still see that you're doing 5 factorial, and then you're not choosing 2 and you are choosing 3. So choosing 2 people to be in your group is the same as choosing 2 people not to be in your group. So there are some similarities with this, and some symmetry with these things. As soon as you say, yeah, these 2 people are in, you're actually choosing the 3 people who aren't in. And likewise, if you choose 3 people who aren't in, you're selecting 2 people who are in. So now we can go back and take a look at the poker question that we had looked at previously, and we can see if we can figure out how many 5-card hands are possible. And when we looked at this previously, we did it as though the order the order did matter. And so we just did, well, you have 52 times 51 times, and we kind of did it as a fundamental counting principle question. But really, the order doesn't matter. When you get tossed the cards, it doesn't matter if the Queen of Hearts comes to you first, or third, or fourth, or fifth. It doesn't matter when it comes to you, as long as you get it. So there's 52 cards in a deck, and out of those 52 cards, just choose me any 5 cards. The order doesn't matter. And again, if you can use your calculator, you can just immediately get answers to these, and you're done. There's about 2.6 million different ways of giving a 5-card hand. that's with order not mattering. Again, we can't use 52 times 51 times 50 times 49 times 48 because things can be in a lot of different orders. Okay, let's take a look at this one. A container has 10 balls in it. 4 of them are green. Let me make this a little more visual. 5 of them are red, and 1 is white. So how many ways can you choose 6 balls so that you get 1 white, 2 green, and 3 red? Okay, so first of all, let's just take a look at choosing 1 white ball. So you have 1 white ball that's in there, that's your N, and you have to choose it, so your R is also 1. That's the first thing that has to happen. So this is like fundamental counting principle meets combinations. There's the number of ways that you can select 1 white ball. Once you've done that, you also have to, so this is basically you're using the word and, which is telling you you need to use the fundamental counting principle. So you also need to choose green balls. Well, there's 4 green balls, choose 2. So this was the whites. Now we're working on the greens. And, so there's a number of ways that you can choose the green balls. And out of the 5 reds, so this will be the reds, choose 3. So I get a total of 1 way to do the white balls and 6 ways to do the green balls and 10 ways to do the red balls, means that there's 60 ways. So we'll definitely be using combinations and fundamental counting principles with some of these harder questions. Let's take a look at one last example, and it's kind of a part A and a part B to this last one, but again, it's a student council question. Presidents, and for this first part, well, the vice presidents are the same. They just help each other, help the president. And then there's 5 what they call members at large. 20 people apply for student council, and how many ways can you take those 20 people and allocate them to these positions? So there are 20 people, and you would choose 1 to be your president. And then you would have 19 people left, and you would choose 2 of them to be your vice presidents. Once you've chosen those 2, there's only 17 people left, and you can choose any 5 of those to be the members at large. So that gives you a grand total, and I would do each of these individually just so you can show your work. 20 times 171 times 6188. That way your teacher can tell, oh, you plugged in one of them wrong in your calculator, and you get an amazing number of just over 21 million ways of being able to allocate people to those positions. Now, if the 2 vice presidents were different, so if one of the vice presidents worked on internal things and another vice president worked on external things like dances and associations with other schools, then those 2 presidents, the situation would look quite a bit different. We would have, well, you'll still choose a president, but now out of the 19, you need 1 person to be the internal, and out of the 18, you need 1 person to be the external, and then out of the last 17, you need 5 of those people, and you'd have an answer. Now, there's another way to think about this second situation. You can go and choose your president, but now here, you want to choose out of 19 people, 2 of them, but the order matters. So if you choose the first person to be the internal and the second person's the external, that's different than them being in the opposite positions. And because the order can matter, you could use P. So these are equivalent. Doing both of the C calculations is equivalent to doing the 1P calculation. And then, of course, you'd have your members at large. You can go and punch these numbers through. They will work out to be equivalent because in one case you're selecting those individual people, and so out of 19 and then out of 18, so kind of order is mattering by the way that you're choosing them. And in the second case, you've got 19 people, and the order matters on how you choose them, because if I choose Amy to be the vice president external, then Sarah's vice president internal is different than if I switch both of those. So the order definitely matters. Okay, we'll get some more practice in class.